Kia ora and welcome to video 10 in the series Insightful Integration. In this question, we are given a couple of features that a graph satisfies, and we need to find the equation of that graph. Passing through the point 3,2 will now enable us to find integration constants. And then the property that any normal to the curve has a y-intercept of 6 is going to bring in a differential equation because, of course, the normal refers to gradient. In fact, when you differentiate something, you get dy dx. That would be the gradient of the tangent. The normal will be the negative reciprocal of that, and that's at any point on the curve. So you end up with a differential equation to solve. You may find that there's a shortcut to this problem. However, to prove it, you need to use integration. All the best, and we'll catch you after the intro music for the solution.
Alrighty, so it might be tempting with this problem if you thought about it, just to write down the answer as a circle. If you think about the properties of a circle, in this case the circle would have to have a centre at y equals 6, but a circle is such that anywhere on the circle, so let's just draw a fairly good circle there, any point on the circle, the normal at that point is the radius, because the normal of the tangent, something like the tangent always meets the radius at 90 degrees, might have been the property you learnt back in year 11 NCEA geometry. So yeah, it's a circle, we're done. We just need to make sure that we get the right radius for the circle because it has to go through the point 3, 2. So if I put 3, 2, I have absolutely no idea on scale on this diagram, and then I go, right, the circle has to have an equation, a general equation like this, and then we'll go r squared because we don't know what the radius is, and then we sub in the coordinate 3, 2, 3 squared plus 2 minus 6 all squared equals r squared, and we evaluate that. That's 9 plus 16, so r squared must be 25. Okay, so the equation of a circle, I'll just make that a bit clearer, so we're subbing in 3, 2 there, r squared equals 25, that is the equation, and then we give some justification as to why that works. It's not really a proof though, it doesn't prove that that's the only curve that has these properties, although it would be kind of hard to draw anything that was different to a circle. So for example, if we started here and then we decided, oh, let's go off on a curve, now the normal is not going to go through the y-axis at 6. So it has to be a circle, but let's use integration and a differential equation to prove it. Okay, so what would the differential equation look like? Well, what we essentially need to think about is some curve, I'm not going to draw it as a circle, with a point xy. xy is a general point on the curve. And at that point, the derivative of the tangent would be dy dx. Okay, so slope of the tangent is dy dx. What did I say? The derivative of the tangent. That doesn't make any sense. What am I on about? But the slope of the tangent is described by dy dx. Now, we know that the normal, again, I don't know that it's the radius of a circle, but the normal would have a slope that's the negative reciprocal of that. Okay, that is what a normal is. It's a line at right angles to the tangent, so negative dx over dy. And that has to go through the point 0, 6. So what I can do is I can find the gradient of that line there using rise over run. The run is x and the rise is y minus 6. Unless y is below 6, I guess we need to consider both cases, but let's just, for simplicity, just go with that, because equating the gradients is going to give us y minus 6 over x equals to minus dx over dy. And there's a differential equation. Use the advice from previous videos. It's probably separable. Yep, it looks separable to me. So if we do that, we've got y minus 6 dy equals negative x dx. Put some integral symbols on it. Y squared over 2 minus 6y equals negative x squared over 2 plus c. Looks like a circle equation appearing. Multiply the whole thing through by 2 just to tidy it up. Let's just use a different integration constant. 2c can be equal to k. Let's find that value of k by substituting in the same point as before, which was, what was it? 3, 2. 3, 2 goes in there. 2 squared minus 12 lots of 2 minus 3 squared. If we work that out, 4 minus 24 is negative 20. Negative 20 plus 9, negative 11. Okay, it doesn't look like our nice radius equation as before, but that's because it's not in the completed square format yet. If we rearrange this, we've got x squared plus y squared minus 12y plus 11 equals 0. And then we complete the square on this dude. Y minus 6 all squared is going to give us 36. We take away 25 from it to get the 11. And then we rearrange it. And there's the equation of our circle that we had before. But we've used integration and a differential equation to arrive at it, proving that that is the only equation that satisfies the properties of the problem.